Hello everyone. Hello everyone. Please join me in welcoming our speaker for today, Aditi. Aditi is currently a PhD student at IIT Gandhinagar, advised by Professor Mishra. So her research interests include computational social studies with focus on matching, voting, and fair division. She's also interested in algorithm design and complexity theory. Today she'll be talking about her work, The Price of Equity for Binary Valuations and Few Agent Types, which is to be presented at the Symposium of Algorithmic Game Theory, September this year. So welcome us. Hello everyone. I hope you can hear me fine at the back. Thanks, Manisha, for the introduction. So today I'll be talking about price of equity. This is joint work with Professor Umang, Professor Lee, and Professor Rohit. So we'll see the problem setting. We'll see the good cases where we don't have to pay any price. Price I define in a moment. And whenever this price is unavoidable, then we'll look at the bounds within which that price lies. Okay, so the setting is as follows. We have some agents, we have some indivisible goods, and all agents have a value for every possible subset of goods. Now the valuations are additive. So in that sense, the entire valuations are incorporated by this n by n matrix. Any bundle of goods, you can just add up the goods of the bundle, the values of the individual goods, and you get the value of the entire subset. So we'll look at additive valuations, and a little bit more, we'll look at the binary additive valuations. So the utilities of the goods are just the sum of the goods. Now, what is the output that is expected? We want an allocation of goods among the agents, which is one bundle for every agent, highlighted by these boxes. What sort of allocations do we want? We want them to satisfy certain properties. One of them is welfare maximization. What is welfare? So welfare is just adding up of individual agent utilities in various ways. So a couple of prevalent notions of welfare maximizations are utilitarian, where you just add up the individual utilities. Then we have Nash, where you take the product. Then we have egalitarian, where you try to maximize the minimum utility, like make the poorer agent happier. That is not the only objective of interest. We also want fairness simultaneously. A couple of prominent notions are envy-freeness, equitability. Equitability will be the main focus of this talk, but just for completeness sake, let me define envy-freeness. These are the allocations in which we don't have any envious agents, and wherein we define an envious agent. So take a pair of agent, and A will look at B's bundle, and he will think that, okay, my bundle is always better than him, and from his perspective. So we call those pair of agents as envy-free, and whenever we don't have any envious agents, we call those allocation envy-free. Correct. You can see that every good is allocated to agents who like them. There is no non-wasteful. There is no wasteful allocation of goods. Everything is given and given to agents who like them, and therefore every agent derives utility out of them. So it somehow maximizes the welfare. Let's see equitability. So in equitability, we want every agent to derive equal utility from their own bundles, from their own perspectives. But what happens, the bad thing with envy-free and equitabilities, they might not exist every time in cases of all instances. So we resort to approximations. And one powerful approximation is you just hide one good from the envied or non-equitable bundle, and then you're good to go. You achieve equitability or you achieve envy-freeness. So that's the concept of EQ1. And in binary valuations, this just falls back to saying that the utilities are either U or U plus 1. They're off by 1. Okay, so this is the concept of EQ1. So this allocation is arbitrary, it is not EQ1 and hence not EQ. Okay, so let's, as Professor Siddharth mentioned, that this allocation is utilitarian, it is Nash, it is egalitarian because everything is non-wastefully allocated. Is it EQ? No, we can see that there is a utility difference between A1 and A3, right? It is not even EQ1 because even if A3 chooses to ignore, let's say, G6 from A1's bundle, then also equitability is not achieved, right? So what do we do to achieve EQ1 in this setting? Let's give G6 to A3. Then it becomes EQ1, right? We can see. But then in the process, what did we do? We lost some welfare, right? Now this allocation is no longer Nash, it is no longer utilitarian, although it does satisfy the, it maximizes the minimum utility, but we lose out on some welfare notions. What is exactly our price that we want to bound?
this could be like really bad. Like, imagine a case where if there are agents who value everything at 0.
Correct.
And there's one agent who has value 1 for everything.
Right.
So you are kind of like you're completely gone. You have to waste the entire grand bundle of goods.
Right. So that's the setting of non-normalized valuations where one agent values the entire thing. But then look at normalized setting where every agent, in non-normalized setting, this price can be very high. Yeah. Okay, so let's define what is this price. So whenever okay, so in the normalized setting, what happens is every agent likes the grand bundle at a constant. So in binary setting, that drops down to saying that every agent likes equal number of goods, right? So the rows in the valuation matrix, they all add up to the same number. Okay, so this price of fairness, by which I mean that how much welfare is lost when you insist on achieving that particular fairness notion, is given by this ratio where we say, okay, take the welfare optimal allocation, take that optimal welfare and divide that by what is the best welfare you can achieve among all the set of fair allocations. And we'll take the supremum of that across all instances. So that is the ratio that will be the focus of this talk. Okay, so whenever this intersection is non-empty, that's the best case scenario, right? You have a fair allocation that also maximizes the welfare. Okay, so now you can plug in your favorite fairness notion here, your favorite welfare notion here, and ask this question: what is the price in every setting? Okay, so let's look at some of the prior works in the setting. So people have looked at envy-freeness, and Karianis and others have showed that an allocation that maximizes Nash welfare, which is the product of the individual agent utilities, is also EF1. So this seems to be saying that when you achieve EF1, you don't compromise on Nash. You can find an allocation equation which is both satisfies both the properties. So that's a good case when price of EF1 with respect to Nash is 1. B et al. Established that for utilitarian welfare, the sum of the utilities, this price is lower bounded by root n and upper bounded by n. And this gap was reduced by Berman and others, saying that the rate is tight. The upper bound is also root n. Recently, there was work of Sun and others who established the price of egalitarian EQ1 as 1 and utilitarian as linearly dependent on the number of agents. Okay, so one common thing about all these prior work are they focus on number of agents. So all the ratios are in terms of n, and they focus on specific welfare notions. What we do in our work is we focus on number of agent types that are defined in a moment, and we focus on not so specific welfare notion but generalized p-mean welfare notions, which encapsulates these specific notions as their subcases.
It is also for normalized, just egalitarian result is for normalized. Okay. It's kind of a small thing, like it's a constant factor, but this is still open, right? Whether the between 3 and okay. These are constraints.
But we'll see that we'll get improved bounds in terms of agent types for utility. We'll get almost correct bounds.
Okay, and this again, like just to get some clarity, like the square root n I know holds beyond additive.
Yes.
These two, the Sun and all, these are also for additive. Or
I think they are for additive.
It's kind of interesting that the egalitarian can be achieved without any.
Okay, so coming to agent types.
You cannot, take my statement. You cannot get the first is it can't be algorithmic because if finding an egalitarian is going to be hard. It be that like the price of equitability is 1. Finding that optimal means you have found the optimal egalitarian.
Right. I think these are not computational price of fairness. These are theoretical
existence.
Yes, existence. Okay, so agent types refers to a collection of agents who value all the goods alike. Right. So, for example, in this instance, the number of agents are 6, but there are only 2 types of agents because all the blue agents like everything alike. Okay. So there can be instances which have like thousands of agents. Now you can make these blue agents as large as you want, but the agent types will remain 2. So that's a potentially a much smaller parameter than number of agents. Okay, so we give essentially tight bounds on number of agent types, and that improvises over the existing bounds. So, okay, and then now coming to these generalized welfare notions. By P-mean welfare notions, I mean you take the utilities to the pth powers and aggregate them by this concave symmetric function. And now when you plug in P equals 1 here, then what you get is just the sum of the utilities, your utilitarian welfare. When P converges, when P tends to 0, this tends to Nash. And when P tends to minus infinity, this is our egalitarian notion. Notice that we'll focus only on P ranging from less than -1. And that's because this range of P-mean welfares satisfy certain Pigoularden principles, which are like nice principles. So which makes a rich agent, which tries to balance out the evaluations among all the agents. It does not make the rich agent richer and the poor agent poorer. It tries to create a sort of balanced allocations, which is our focus in fairness. Right? So we'll focus on these P-mean welfare notions for P less than equal to 1. Okay, so the results, quick summary of the results is as follows. So we'll show that if you look at all these bounds, they are just constant factors away. And we saw previously that for egalitarian, as Professor Sanath was also pointing out, there was a factor of 3. But what we show is when we do it in terms of agent types, then we achieve almost tight bounds in that sense. Okay, so let me quickly go to the low bounds thing and show an intuition how we achieve these low bounds. Okay, so this is the kind of for low bounds. What we do is you have to show just one existence of one instance, which shows that, okay, in this particular instance, you have to have this loss of welfare. There is no algorithm that can give you better welfare, simultaneously giving you fair allocation. So let's look at this instance over here. We have this W plus 1 agents of same type, and the remaining agents are of different types. Each of these MIs are a bundle of W goods each. Okay. Now, when you want to allocate the goods, you can allocate like one good each from this bundle over to these agents. But here, there is one extra agent sitting over here. He will be empty-handed, right? No matter how you allocate these goods. And now, what you can do is you can give this signature bundles to these agents over here, right? This allocation allocates everything non-wastefully. Therefore, it optimizes welfare for every P less than 1 welfare notion. Okay, but this is clearly not EQ1, right? Because there are so many goods here. Whenever we go to EQ1, you have to lose all these ones over here. Because there is an agent sitting over here who has 0 utility that bounds every other agent's utility to at most 1. So that's our EQ1 allocation. And now, what is the low bound on price of equity ratio? It is just the P-mean welfare in the numerator, where these W agents are getting utility of 1 and R minus 1 agents are getting utility of W. But as soon as you drop down to an EQ1 allocation, this W drops down to 1. Right? So this is our general function for the low bound of price of equity. And now what you can do is, for different values of P, you can choose W. W, just to recall, it was just a normalization constant, right? How many goods every agent likes. You can choose different Ws. Here S is just R minus 1 for simplification purposes. So for every different values of S, you get these different low bounds. I'll skip the calculations here. They are quite non-trivial, but I hope the intuition is conveyed, right? Where the welfare loss is coming from. You could allocate it to him, but it won't bring any utility to him.
Yes, but that means the other people can get more.
No, but then you look at utility of this W plus 1 agent. He is still at 0 utility, right? So therefore now every other agent can have utility of at most 1. In equitability, you compare the utilities. Okay. If there was a good sitting over here which is valued by W plus 1, and if you allocate that good to him, then his utility becomes 1, and now you can allocate at most 2 goods to everyone else.
Planted like this idea that there's one agent that's stuck at 0.
Okay.
And because of that, every other agent is stuck at 1.
Okay. Okay. So if the intuition is clear, let me move on to the upper bounds. Let's look at an easy case of 1, which is a sum of the utilities. Let K be the rank of our input instance. By rank, I just mean the number of independent columns or independent rows. Okay, let's say B is the allocation that maximizes the utilitarian welfare. We'll claim that the number of wastefully allocated goods, the goods which are allocated in such a way that leads to the loss of welfare, are at most this much. Where M is the total number of goods. Suppose this statement is true, then what happens is this allocation B, at least M by K goods are allocated non-wastefully, which means that B has at least this welfare. So if you look at the ratio now, this is just the optimal utilitarian welfare, which is equal to M. Like every good, if it is allocated non-wastefully, that is the best welfare you can achieve. So M by what is the best equivalent utilitarian welfare? It is at least M by K. Right? So this ratio gives us that the POE is at most K, which is the rank of the instance. Now it is easy to see that rank is also lower bounded by number of agent types. So that gives us a bound of R on utilitarian welfare. We saw that it was R minus 1 as a lower bound. So these are tight bounds for utilitarian. Let's move on to feel. Okay. Let me just clarify this statement also. Why do we say that this claim is true? Suppose this is not true, right? Then what happens is there will exist an agent I which will value. So consider a good which is wastefully allocated, right? A poor agent who has a utility of 1 less in the equivalent allocation cannot value this good. Why? Because if he does, then that good can be allocated to that poor agent, increasing the utilitarian welfare, right? But you started off with an allocation that maximizes that welfare. So that is not possible. So every poor agent values a wastefully allocated good at 0. Then it means that agent likes strictly less than these many goods. So in equivalent allocation, in the case of binary setting, agents can have only 2 utilities, either say U or U plus 1. So the agents with U are poor agents. Okay. So since agent I likes less than M by K goods, then by normalization, every agent likes exactly the same number of goods. So every agent will like strictly less than M by K goods, which means that there will exist a good for which every agent has value 0. But then we start off by the assumption that every good is valued by somebody. Otherwise, you can just throw off that good in the very beginning of the input instances. So that's a simple argument for P equals 1 case.
Can I look at this slide?
Yeah.
30 seconds. It's not big.
The rank can be small even if the number of types is large.
Yes. Actually, no, right? Like for binary matrices that are row sum are fixed, the rank will be equal to the K equals 1. You're saying that if
So they will get a combination of them.
how do you get the second implication? So you look at a poor agent and argue that I'm just trying to fill this jump that was a bit too quick for me.
Okay.
How are you saying that agent I likes less than M by K? I is a poor agent.
Yeah, right. Okay. So, So what are the number of wastefully allocated goods? There are at most M minus M over K. What are the remaining goods that are there? M by K goods, right? A poor agent cannot like all these set of M minus M over K goods. So he likes at most M by K goods.
Okay, but how do you know that all you're using this part that rank shows up, that doesn't click? Fine, I see the implication. So if an agent I is poor, then it will like less. None of those wasted goods will be liked by it.
Right.
Great.
Right.
Okay.
This is the binary setting.
Why is rank an important feature here? That
I think you can choose to ignore rank as well. You can even focus on, let's say, agent types.
Yeah.
And that will work.
there is no linear algebraic property.
Right.
So I see. So yeah, just bear with me for a few minutes. So agent I has, let's say, utility U, valuation U, and there are M by K goods that are wastefully allocated. I'm just picking a new number U in the, which is the,
Correct.
so I give you a allocation EQ1 and the valuations are U and U plus 1.
Yeah.
And so now the point is every good that is wastefully assigned is not liked by any of these agents.
Yes.
Agreed. But then the point is that the number of goods that I likes is actually less than U, or it's actually, it can be exactly U and not M by K.
So that U will also have to be less than M by K.
Oh, if it's more than M by K, then you get sorted.
Yeah.
That's also one point. U has to be less than M by K and yes. Okay.
You can never be more than the number of goods an agent like, because that's the utility that he derives from the like set of like
That's
goods.
true, but yeah. I mean, what I'm saying with what could happen is that U is much larger than M. So I mean the second bullet holds when like the total welfare is less than that.
Correct.
Like, you could have U as 10 million.
Correct.
But then fine. Okay. Sorry.
Every event likes strictly less than N by K goods, but the number of agent types is R, not K, which can be more than. So,
Yeah.
how are we taking the contribution in the last place?
So the number of agent types can be more, but we want an upper bound.
So, how are we taking the like?
Okay, so the contradiction is on the fact that if that happens, that every agent likes is strictly less than M by K goods, and there are so many types of agents, then there can be like so there will exist a good G star which is not valued by any of these agents.
I think more than suppose I is so then how are we taking contributions?
I think you can, for simplicity, you can replace rank by agent types as well. And then this ratio becomes M by R. And if you multiply M by R over by R types, then there are less than M goods, which are just right.
Yeah, you will have to do that.
Yeah.
Otherwise, for JVC is pointing out this.
Yeah.
Right.
Yeah.
Let me just bother you for 30 more seconds on this.
Okay, so let me move to the upper bounds for P less than 1. So this is a
M being the number of goods.
M being the number of goods. So this is a known result by Balabu et al. Which says that if A star is an allocation that maximizes the Nash welfare, then it also maximizes any strictly concave symmetric function. Now what happens is the P mean welfare that we are looking at happens to be concave symmetric functions, but not strictly. So we can't really use the statement directly to start with a Nash welfare allocation and say that it does that. But what we can do is we can modify the Balabu et al. Proof of this statement and show that A star, which is the Nash optimal allocation, also maximizes the P mean welfare for all P less than 1. Right? So there is this one unique allocation that does our job. So we get the numerator of our price from this. Now what we do is let's start with that optimal allocation and truncate it to find an EQ1 allocation from that Nash optimal allocation. How that truncation is done is, suppose this is the A star with which is not EQ1 to begin with, which has like different utility levels for every agent. What we do is you take the minimum utility of any agent, add 1 to it, and then truncate all the remaining extra welfares and allocate all these goods wastefully among all the agents. So now the utility profiles look something like this. This is EQ1, right? So we have done some wasteful allocation by doing this. And also, you can always find an agent who will not like these goods, again by the same argument previously, because if they liked that good, then it could have been previously allocated to that poor agent, increasing the national welfare. So this thing is possible. We can convert A star to an EQ1 allocation, losing some welfare. Now let's try to bound that welfare. Now, okay, so since B is coming from a Nash optimal allocation and it has same number of these richer agents, right? By richer agents, I mean with the longer bars. Whatever number of agents here we have of utility more than U plus 1, that exact number is reflecting over here, right? So since A star is Nash optimal, it maximizes the minimum utility as well. Therefore, B also maximizes the egalitarian welfare among all EQ1 allocations. We can also show that B also maximizes all P-mean welfares less than 1. A quick argument is as follows. So we just saw that these number of agents who have utility U plus 1 are equal. Let's call them the rich agents. The number of rich agents is n rich. Now, since A star is Nash, A star is also Leximin, which is to say that it maximizes the minimum utility. Subject to that, it maximizes the second minimum utility, so on and so forth. So when it does that, there can be no allocation in which every agent has value at least U and have more than n rich of these richer agents. Okay, so now if C is any other EQ1 allocation, and if this is true, that if every agent has at most U under C, then B beats C anyway, right? Because B has greater welfare for every agent than C. Then C cannot have a better welfare than B. Suppose C has at most n rich agents because that is the maximum number of richer agents it can have, and at least those many poor agents have value at least U under C. Then it is exactly B, right? It is in some sense you can just rename the agents. Up to renaming it is isomorphic to B in some sense. So that would suggest us that B maximizes any symmetric non-decreasing function of agent valuations. So that says that to bound that ratio for the generalized P-mean welfare, you just have to look at the A star Nash optimal and the truncated B allocation. So you plug in the values of the P-mean welfares here and we get the bounds. Again, I'll skip the calculations, but whenever we plug in the appropriate substitutions in the previous ratio, we get these upper bounds as follows.
So actually, this Benabao thing was in fact strengthened version by Babayev and Feige. Again, third author as well. But it's sort of the point is these are majorizing allocations, like Lorentz dominating. You can generalize this to like beyond binary additive to like binary submodel. So
right.
rank functions as well.
Yeah, I think the upper bounds hold for binary submodel as well.
Yeah, so this in particular does.
Yes.
So the majorizing argument.
Right. Okay, so now we have seen the bounds. Let me just move on to a case which is a good case where there is no price of welfare to be paid. So this is the setting of doubly normalized binary valuations. By that I mean we saw normalization, right? All rows add up to the same constant. Now we want every column to add up to the same constant as well. The two constants can be different. Okay, so now we have two cases here. Suppose the number of goods is an integral multiple of number of agents, right? Then what we can do is we'll claim that there will exist a non-wasteful equitable allocation, let alone EQ1 will give you an even better EQ allocation. Every agent receiving an equal utility of C, okay, which is the multiple.
Conics theorem.
It's Conics theorem, or you can say it's a generalized Hall's theorem. You can use
There'll be C number of perfect matches.
Correct. C number of perfect matchings, or you can see them as C stars. So here in this example, since every subset here has at least C times that size of neighborhood sitting over here, you can allocate exactly C goods. Here C is two goods to every agent. And by that simple argument, you get an EQ allocation. The problematic case is when we have some extra goods over here. Now we can allocate these goods equitably, but what do we do with the remaining Q goods, right? So here we use this very known, nice eating sort of an algorithm, which was given by Bhugalmani and Morgan. So, okay, so let me see. Let's consider this instance where the number of agents is not an integral multiple, number of goods is not an integral multiple of number of agents, and the valuations are doubly normalized, right? So we have 3 ones here, 2 ones every column. What we do is we first try to create a square matrix. So we create agent copies. So here there are 4 agents. So we can add like 2 dummy goods over here. So that there are 8 goods and create 2 copies of every agent. So there are 8 agents. Every agent copies value the good alike. Now what these agents do is they start for every time interval, they start eating their favorite goods. So the Bogolmania probabilistic serial algorithm was valid for ordinal preferences. So there is a ranking, a strict ranking you can break ties arbitrarily, and the agent starts feeding on their most favorite good. Here we have 0 and 1s, right? So here the slight twist is that an agent eats all the goods simultaneously, all the goods which he value at 1. Okay, so here agent 1, he values these 3 goods. So he eats these 3 goods simultaneously, 1/3 of each of them. All the other agents are doing the same thing. The first copies of the other agents during the first time step are eating 1/3 of the goods. Okay, now see that the row sum is always 1 here, at least in the first time step. Now what happens is, let's look at G1. 2/3 of G1 is consumed in the first time step. 1/3 remains. It is liked by 2 agents, A1 and A4. So that 1/3 breaks down into 2 parts. Among all the remaining agent copies do the same. Now, because of this doubly normalized structure of the evaluation matrix, each of the liked goods, each of these goods which are liked by the agents, the non-dummy goods, are consumed at the same time step, right? So all of these agents, now we want these second agent copies also to eat 1 unit of good in the last time step, but right now they have eaten only half of the goods, right? 3 times 1/6 adds up to half. So they can eat half of Okay, now this matrix is nice. Every row sums up to 1, every column sums up to 1, which is called as doubly stochastic matrices. Now we can use this Birkhoff-Neumann decomposition and represent this matrix as a convex combination of permutation matrices. By permutation matrices, I just mean that every entry is 0 or 1, and it is doubly normalized. Every row and column adds up to 1. Okay, so these permutation matrices give rise to a corresponding allocation here. You can allocate the good where 1 is there to the agent copy, right? And just plug and just bring in the agent copies back together. So okay, this is the corresponding allocation. Now here you see that the point is that dummy goods get allocated to different agent copies because all the agents start eating the dummy goods simultaneously, and only the last copy of the agents start eating the dummy goods. So these dummy goods, however many number of them, they are nicely distributed among all the agents. There is no agent who receives 2 of these dummy goods, right? So therefore, this in this allocation, the utility of the agents only differ by 1, right? Whoever receives a dummy good will be the poor agent with the utility U, and rest all will be the richer agents with utility U plus 1.
This is similar argument that Aziz et al. Has for the ex ante.
Correct.
But I mean, there is a flow interpretation to it. Like you can look at that, like the bipartite graph you drew and argue that there's a flow which is kind of has this nice property.
Okay.
So it will give you like a fractional matching from which you
can derive a difference. Okay, so this was all regarding the bounds and the good things for additive valuation. Moving on to submodular valuations. Submodular valuations are the ones which follow this diminishing gains property. So if there is a larger subset and you add a good to it, it brings lesser utility as compared to you bring that same good to a small size subset. For those submodular valuations, we see that for identical, if they're identical, then price of equity is 1. Otherwise, for binary submodular valuations, binary, I mean the marginal gain that you have is either 0 or 1. The price of equity is n over 6. It depends, and this is true even for 2 agent types, right? So even when agent types is low, we can't really improve by bringing them down the ratio to depend on the number of agent types. It is linear in terms of the number of agents. So that's the one change from going from additive to some modular valuations. And here we show, and this is true for P equals 1. And for submodular valuations, we have an upper bound of 2n for the entire P spectrum. Okay, so the takeaway from the talk is the two things, that is obtaining bounds in terms of a smaller parameter, and for upper bounds, this again reiterates the fact that Nash optimal allocations are the way to go, which means that you start with Nash optimal, truncate it to EQ1, and then that is your most fair, welfare maximizing allocation that you can get among all the instances.
It's to an upper bound or
I can talk about the lower bound, which I'm currently recalling. What we do is we treat every good as a vector, like microid valuations, and we create the similar kind of instance that we had earlier. There are signature goods, and then there are a couple of agents to have this.
these are like the submodular functions you create are actually rank functions. No?
Yes,
Oh, have to be, sorry.
the microid rank.
Yeah, binary search. So what is the maker again? Like just a like a linear maker. So
Yes, yes. Any questions?
So what is the so get the permutation matrix combination? What is do after that?
Okay, so yeah,
Is that the
right. So you can take this matrix, decompose it into some number of combination matrices, right? And that's a matrix combination. So you have weights, and all those weights sum up to 1. You can pick any permutation matrix. The probability comes from the weights. From any probability distribution, you can take that matrix, and we'll say that that matrix is EQ1. No matter which matrix you take from the permutation, it's a random matrix coming from that permutation. Because
everything in the support is
respects EQ1. Everything is Aditi, for the wonderful job. Thanks so much. I think I skipped all the calculations, and they are like they involve some non-trivial calculus. But if you want to get in touch, I can explain. And the slides for this.